These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There is a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. By the way, I also offer tutoring via Skype, and you can find more information about that Skype tutoring service at my website. Thanks. Okay, well, what we need to go over now is the reactivity of this kind of molecule. Can you think of any kind of nomenclature for this general type of molecule that I have on the board?
Beta, unsaturated, ketone. Or aldehyde, sorry.
Right, so we have an aldehyde and it's unsaturated. Remember, as we talked about last time, what does unsaturated mean? Well, basically it means this pi bond. The unsaturated means this double bond here. Now, which two atoms is the pi bond between? It's between the beta atom and alpha. So the name that's conventional is the alpha-beta unsaturated. This would be called alpha-beta unsaturated because, of course, if you have a double bond, it has to be between two separate carbons. And as usual, we would call this the beta carbon, this the alpha carbon, and this is what we could call the carbonyl carbon. This is the carbonyl carbon, then alpha, then beta. So we could call this an alpha-beta unsaturated aldehyde. And alpha-beta unsaturated ketones would behave very similarly. Now, last time we saw a way to make alpha-beta unsaturated aldehydes and ketones. Do you remember what type of reaction makes this type of formation?
Aldol?
Yeah, our aldol condensation. That's right, under cold or hot conditions.
Hot.
Yeah, that would be hot conditions. Which category reaction is that?
3.
Yeah, that's our category 3, where the nucleophilic atom attacks the carbonyl or former carbonyl twice. Who's the nucleophilic atom in an aldol condensation?
Another carbonyl.
Who's the nucleophilic atom?
An enolate. The carbon. Alpha carbon.
The alpha carbon, that's right. The nucleophilic atom is that deprotonated alpha carbon that's in the enolate. In an aldol condensation, the nucleophilic atom is the deprotonated alpha carbon in an enolate. And we know that who was the electrophile? The carbonyl that it attacked. So, how did we make this out of an aldol condensation? Well, this must have been the nucleophilic atom. So who was the electrophilic atom that it attacked?
The carbonyl carbon.
Which carbonyl carbon is that it attacked?
Beta.
This over here?
Yeah.
Now, if this was attacked, it wouldn't be a carbonyl anymore. It would look like this, wouldn't it?
Beta carbon.
This is the carbon that used to be the carbonyl carbon over here. Of course, it doesn't look like a carbonyl carbon anymore because it's been attacked so many times that the oxygen got blasted off. You can see that from our general category here. The oxygen here has been blasted off as a hydroxide. And we saw that when we're doing the aldol condensation, it's helpful to keep putting in the alpha label and the asterisks to remind you who used to be the electrophile and the nucleophile. So that would be helpful if you're doing a retro aldol condensation here. So this carbon over here must have formerly been a carbonyl carbon. In particular, this must have been formaldehyde that got attacked. This carbon over here used to be this formaldehyde carbon, and then it got attacked by this alpha carbon to give us a category 3 type reaction. Well, that's the kind of thinking you have to go through if you're going to do the retro aldol condensation, but we decided we won't do a lot of practice with that right now. But anyway, here we have a alpha-beta unsaturated aldehyde or ketone, and we know that we can get those from aldol condensations. Now, the next thing we have to figure out is what can we do with this type of molecule? Now that we know how to make it, we want to know the reactions that it can undergo. Well, first of all, where would be a logical place for this nucleophile to attack?
The nucleophile, the carbonyl carbon.
That's right. We've seen many examples of that already. Why is it logical for this carbonyl carbon to be an electrophile?
It's delta positive.
That's right, because it's delta positive. We've talked about that quite a few times. We've also mentioned, however, there's another important reason why this carbon is electrophilic, besides the fact that it's delta positive. What was the other explanation we can give?
Resonance.
That's right. There's a resonance structure, remember, where there's a full positive charge on this carbon. And that also explains why this carbon would be electrophilic. We talked about how for this second semester of OChem, it's really important for students to get into the habit of using resonance to form explanations for things. Anytime there's possible resonance structures, you have to look for a way that you can use resonance to explain things, even if the word resonance hadn't appeared yet. It's our job to bring that in. All right, now the complicated thing is that in an alpha-beta unsaturated aldehydroketone, there's another electrophilic atom besides the carbonyl carbon. There's another atom here. Which atom is the other electrophile?
The alpha.
This one over here?
No, sorry, the beta over there.
This one over here. That's correct. It turns out that the beta carbon is also electrophilic. That's the big new reactivity that we didn't have for normal aldehydes and ketones. In a normal aldehyde or ketone, the beta carbon isn't electrophilic, but it is in an alpha-beta unsaturated aldehyde or ketone. This double bond makes this electrophilic. So the first thing we have to do is explain why it's reasonable for this carbon to be electrophilic.
Because of resonance?
That's a good explanation. How does resonance help us to explain that? Let's try drawing another resonance form that would explain why this is an electrophile. That would be a good test question. Let's try to draw another resonance form. For this molecule that explains why the beta carbon is electrophilic. Good. You want to use electron pushing arrows to show that you got that. Okay. Now there was a suggestion that we should do this. Now the problem with that is neither of these carbons is more electrophilic than the other, so why should this alpha carbon want to hog all the electrons to itself? There's no real motivation for moving the electrons this way, so this would not give us a very significant resonance structure. We don't normally, when we have an alkene double bond, a carbon-carbon double bond, we don't normally have one carbon take all the electrons to itself. However, this would be very reasonable. Why is it reasonable to move the pi bond onto the oxygen over here? Because the oxygen is more electronegative than this carbonyl carbon. So this is a very reasonable arrow because we know the oxygen would prefer to have more electron density than this carbon. And then, now it makes sense to move this pi bond over here to kind of fill the gap that's being left by these electrons. To fill the gap that's being left by these electrons, now we can move this pi bond over to here. That gives us a resonance structure that looks like this. Does this explain why the alpha carbon, does this explain why the beta carbon would be electrophilic? Yes, because it's got this positive charge. We know that positive charges make things into electrophiles. Positive charges make things into electrophiles. This is the kind of logic that you can expect to have to use on the next midterm. There's a good chance you're going to see up some problems where you're expected to explain a reaction you've never seen before. You're going to start seeing cases where you're expected to explain things you've never seen before, to explain why things are nucleophilic or electrophilic. Well, even if you've never seen it before, you can still draw resonance structures that might help you to explain why things are electrophiles or nucleophiles. So now we've been able to explain why this beta carbon is electrophilic because of this resonance structure over here. Keep in mind that carbon-carbon pi bonds are not usually electrophilic. Last semester we saw that carbon-carbon pi bonds are usually nucleophilic. We saw that with all the electrophilic additions that we did at the end of last term. But this behaves differently from a normal carbon-carbon pi bond because it's got this resonance structure with the carbonyl. So rather than being nucleophilic, the beta carbon is electrophilic. And this resonance structure explains that. But if there was no resonance, it wouldn't work that way. This carbon is not electrophilic. This carbon is not electrophilic because there's no important resonance structures where there's a positive charge over there. And this beta carbon is not electrophilic either because, again, there's no resonance structures that put a positive charge there. It's only the alpha-beta unsaturated situation next to the carbonyl. So now, in a sense, that's bad news, because now this makes these problems more complicated. Anytime we have a nucleophile and an alpha-beta unsaturated aldehyde or ketone, we have to figure out, is the nucleophile going to attack the beta carbon or the carbonyl? So we need to have some way of figuring out, are we going to be attacking the beta carbon or the carbonyl? If we attack and we need some names for those. If we attack the carbonyl carbon, that's called a 1,2 addition. When we attack the carbonyl carbon, that's called a 1,2 addition. reason that's called 1,2 is because it's mainly going to involve these two atoms. And they're right next to each other as if they were in a number 1 and a number 2 position. On the other hand, if the nucleophile attacks the beta carbon, we call that a 1,4 addition. When the nucleophile attacks the beta carbon, that's a 1,4 addition. That name is actually a little bit hard to understand. It's not actually a very good name, I think. 1,4 addition is not really a very good name for that. However, we'll just kind of memorize that when we attack the beta carbon, it's called 1,4, even though ultimately the product is mainly going to involve these two carbons over here. Our product is really mainly going to involve these two atoms, which are really right next to each other. In a sense, it seems like we should also call this 1,2 addition, but that's not the way it's named. For technical reasons, this is called 1,4 addition.